In this video, we'll do a couple of applications and models of exponential and logarithmic functions. In the first example, we're going to look at Newton's law of cooling. It says T of t equals a e to the kt plus t sub s. In this particular case, the lowercase t is time. A is the difference between the initial temperature of the object and the temperature of the surroundings. K is the constant, which is the continuous rate of cooling of the object, and T sub S is the temperature of the surrounding air. So let's take a look at an example. Let's say we have a pot of boiling soup with an internal temperature of 100 degrees Fahrenheit that was taken off the stove to cool in a 69-degree Fahrenheit room. After 15 minutes, the internal temperature of the soup was 95 degrees Fahrenheit. Use Newton's law of cooling to answer the following. So we're going to start, I'm going to write down that Newton's law of cooling that we had on the previous slide. So we have it here for reference. So we have T of t is a e to the kt plus t sub s. And because it told me that A was the difference between the initial temperature, T sub 0, and the surroundings, T sub S, I'm going to write it like that. So I'm going to have T of t equals T sub 0 minus T sub S e to the kt plus T sub S. So let's identify some of our pieces. Our 100 degrees Fahrenheit is our initial temperature, or our T sub 0. Our 69 degrees is our surrounding temperature. Our surrounding temperature was T sub S. In 15 minutes, so that's a lowercase t, the temperature is 95 degrees. That's a T of 15, the temperature at 15 minutes. So we're going to write T of 15 is 100, our initial temperature, minus 69, e to the kt, but t is 15, plus 69. And we know our T of 15 is 95. So we have 95 equals 31 e to the 15k plus 69. Subtracting 69 gives us 26, and we'll divide by 31 is e to the 15k. And then we'll take the natural log of each side. So we'll take the natural log of 26 over 31 equals 15k times the natural log of e, which we know to be 1. So k is the natural log of 26 over 31 divided by 15, which is approximately negative 0.01173. So we haven't written our model yet. We needed to know what that k value was, and then our model is going to be T of t equals 31, that was the difference between the initial temperature and the surrounding air, e to the negative 0.01173 times t plus 69. So this is our model. And then we can start answering some questions. To the nearest minute, how long will it take it to cool to 80 degrees Fahrenheit? So we're going to put in our 80 for our temperature at time t and solve for t. 31 e to the negative 0.00011. Sorry, I made a boo-boo. 0.01173t plus 69. If I subtract 69, I get 11. 31 e to the negative 0.01173 t, and I get 11 over 31 equals e to this power, and then I can take the natural log of both sides, and I'll end up with the natural log of 11/31 is negative 0.01173 times t. It did have the natural log of e after that, but we know that that's 1. And then we divide, and we get t is approximately 88.33 minutes, or to the nearest minute, the soup will cool to 80 degrees in 88 minutes. 80 degrees Fahrenheit. Well, let's answer the question differently. To the nearest degree, what will the temperature be after 2.5 hours? Well, since we did this whole thing in minutes, 2.5 hours, 2.5 times 60, is going to give us 150. So we just need to plug in 150 for our lowercase t, or our time, 31e negative 0.01173 times 150 plus 69, and we're going to get approximately 74.34 degrees, or 74 degrees to the nearest degree in 2.5 hours. So that's an exponential model. The next model that we have is example 12, modeling tablet sales. This is a logarithmic model. So in this example, the table gives U.S. tablet sales in millions for several years. This in millions here, we're going to underline that. That's going to become important. The data can be modeled by this function. F of t is 20.57 natural log of t plus 10.58, where t is greater than or equal to 1. And t is the number of years after 2009. So that means, let's put a little extra column in here, 2010 is going to be year 1, 2, 3, 4, and then 5 for 2014. Use the function to estimate the number of tablets sold in 2011, and how does it compare to the actual figure of 24.1 million. So we're going to use this 2, and we're going to find f of 2. Plugging this in, we get 20.57 times the natural log of 2 plus 10.58, and we get approximately 24.84. Don't forget, this is in millions. So this is a little higher than the actual here, but it's close. I know it's hard to say that 3 million is close, but it's not off too much. If the trend continues, when will the annual sales reach 58 million? In that case, in for f of t, we'll put 58 for 58 million, and then we will solve for the t value. And remembering that that is going to be years since 2009. So I'm going to start by subtracting the 10.58, 47.42 equals 20.57 times the natural log of t. We'll divide by 20.57, and we'll have the natural log of t. And then we'll just convert this to exponential form. E to the 2.305 is t, which is approximately 10.03 years after 2009. So if we go to 10 years after 2009, we'll say in 2019, sales will reach the 58 million. So that's just 2 examples of exponential and logarithmic models. We use the models for very large and very small numbers. Logarithms help us do that. So just 2 examples. There's many, many. If you wanted to look up some more, I encourage you to do that. That concludes this video.